The last topic we're going to cover now in this course is all about inductors. When we started our section on capacitors, we said that capacitors were very useful circuit elements because they stored energy in an electric field. An inductor now is a circuit element which is useful because it stores energy in a magnetic field. An inductor is a coil of wire, a solenoid, and I have some in the picture here. An ideal inductor will have no resistance, and all of the potential across a solenoid will be an induced potential. The circuit symbol for our inductor is a bunch of kind of spread out coils a bit. Imagine a slinky that you've pulled apart a little bit. Capacitors have a capacitance, which is charge over potential. We say that inductors have inductance. Inductance has a symbol of L, and it's equal to the magnetic flux divided by the current. So it's the flux to current ratio because the amount of energy stored depends both on the magnetic flux and the current through the inductor. The units of inductance are henries. So a capital H, which is equal to a Tesla times a meter squared divided by amps. The next thing we'll do now is find an expression for our inductance. Finding our expression for inductance, we're going to take the fact that our inductor is like a solenoid. It has a length L. It carries a current I. And it has N coils. Okay, so when we covered solenoids, we said that a solenoid with these parameters will have a magnetic field going through the center equals mu naught times N times I over L. And we found that result by considering Ampere's law. So in our inductor we have shown on the picture, I'm going to say that the current comes up from in back and around down in front. I know it's hard to draw 3D. That leads us to a magnetic field if we use our right-hand rule. That's going to point towards the right, and it will only exist inside of our inductor if we're assuming that it's ideal. Now the definition of inductance is that it's the magnetic flux per current. So inductance L equals magnetic flux divided by current. And what we mean by phi, the magnetic flux, is the total magnetic flux through the entire solenoid or inductor. So our total magnetic flux would be the flux of one coil times however many coils you have. So our total flux is N, the number of coils, times the flux through any one coil. Let's remember what flux is equal to. So flux through a single coil is going to be B times the area. The B and the area are parallel, so B dot A is going to be B times A times cosine 0 equals B times A. So B times pi r squared. So then the flux through any one coil will be B times pi r squared. The flux through all of the coils will be N times that value. And we'll fill in what we know the expression for B is. B is mu naught times N times I over L. Multiply that by pi r squared. And we're left with the expression for the net flux through the solenoid or the inductor. Mu naught N squared I pi r squared over L. So then that tells me then that my inductance L is equal to my net flux divided by the current I. So L is equal to mu naught N squared I pi r squared over L, all divided by I. You see that the current cancels, and we're left with our final result, L equals mu naught times N squared times pi times R squared over L. So the inductance of any particular inductor depends only on the physical parameters of the inductor. How big is it, how long is it, and how many coils does it have? Start with a simple question. What is the potential difference across an inductor if the current is constant? I'm going to invite you to pause and answer for yourself first before you unpause. Okay, now you've had to think about it. So let's remember the first thing we said about our inductor. An ideal inductor has a resistance of 0. So according to Ohm's law, the potential due to the resistance of the device would be V equals IR equals 0. And our induced potential, which comes from Faraday's law, minus d phi dt, a changing flux comes from a changing magnetic field. A changing magnetic field comes from a changing current. So if current is constant, field is constant, flux is constant, so the induced potential is also 0. So the net potential difference across any inductor with a constant current equals 0. Okay, this sets the stage to tell us that inductors are important parts of a circuit when a current is changing. So inductors are going to be really important if we ever have capacitors that are charging and discharging, and also in AC or alternating current circuits.